Today, I would just like to go ahead and go through some piston profiles. And this is a basic information. I thought it was something that's kind of really nice to see how they've changed over the years. And so the first page here is basically, it's just a broad overview. But if you have any questions later, here's my contact information. And please hit my email if you got questions later. If you want something like this presentation or something, I could send it to you. So just let me know if you have any questions, please. The next slide is just some information, and it's just information for me, so you kind of know who I am. I'm a Christian. I'm a father and a grandfather. I used to drag race a lot. I really enjoyed that. Basically muscle cars and super comp. Worked with a lot of shops. Really enjoyed that. I'm a mechanical engineer. I've been designing pistons since the late 80s. I've got a few patents. I know how to manufacture from top to bottom as far as foundry, forging. I've done a lot of tests. I worked a lot with OEs and OE aftermarkets as far as their service replacements. So have a lot of dyno work. Some of them are, like 50, 100, 300-hour durabilities. A lot of these are exactly what an OEM would go through, and so they would ask the same thing. So I learned a lot with that, and of course we do a lot of in-field testing too. 500 plus piston applications, everything really from Jasper, and probably the last many years are clean sheet design. One thing at Jasper we have to do is a lot of times you only could go to the OE or get an OE parts, or you get an OE, or you get a part that looks like an OEM and it's made somewhere else and you don't know exactly where it is. It may look right, but a lot of the nuances for the actual design for making sure that you don't have excessive blow-by or problems, there's a lot of lost art since a lot of this stuff has left the United States. So what I used to do a lot in Federal Mogul, I brought a lot of it here, and that's what we're doing. I enjoy motorcycling. I love to go ahead and try to make solutions out of problems, and I love working at my little shop that I have. So that's a little bit of my background. This is just kind of give you an idea. Like, I'll have to go through these kind of fast. As you can see, there's like 27 pages. We can get in detail later on if somebody needs to, but I kind of like to take you through, like the 1920s to the 1980s, and then what the big changes that went in the late 80s and 90s, and then around 2000 and up to where we are at now. So, you can look at this. One thing that I used to go to a lot of shops, they would measure the piston and they would put their own clearance, what they thought it should run. This is where you really need to get into the piston manufacturer and find out where the size point is of the piston and how to measure it. You need to know that so you can know how much that you're going to actually put into it. And you also need to understand that these pistons, when you measure them, especially since we're talking about aluminum pistons, you really need to have those acclimated to 68 to 72 degrees. You'd be surprised somebody just holding a piston, for 5 minutes and measuring it. Or if you've got a shop and, and it's really hot outside, so it's hot inside, if you don't have cooling, how much that would change in aluminum, because aluminum expansion is 3 times the amount of steel of cast iron. So these are the things you really kind of need to know. Piston manufacturers on whole build in the clearance that they want you to run on your application. So if, for an example, if they had a 4-inch bore, standard 350 Chevy new engine or whatever, or 6.2, or let's say 6-liter LS, you're going to, I want a thousandths minimum clearance usually, and then so my piston will be 3.990. So they're already cast in, and the deal is you need to make sure that, because a lot of the aftermarket, they can go ahead and if they want to put another extra thousandths or 2,000ths clearance in that to open up their bore, they better be looking at making sure what their ring gap is going to be. So that's where a lot of performance shop has to have, file to fit rings. And you got to remember, if you decide to put an extra 2,000ths clearance in there and you don't use file to fit, you just increased it by pi every thousand. So now your gap went to another 6,000ths. So these are the type of things you kind of need to know. There's a lot of places that used to be, when they did pistons, they would say some would measure at the top of the skirt, some would have it at the center line of the skirt. Depending on the piston, some would put it at the bottom of the skirt. How I've always made pistons and continue to make pistons is I want the largest stiff point of that piston to be my size, because that's where the true size is. And we'll go through the type of pistons and how they have shaped. You also got to remember that everything from the mid 80s, talking about from OE now, were always cam ground. So they're always grind pistons. And so the barrel profiles and all that were basically non-existent. So this is how they have to end up doing it. And we'll go through a few of these. Here's some of the old grinds that people would use. So you got an A, B, C, D grinds, and you can see the center line of the thrust face. I don't know if you can see my arrows, but you see the center line of the thrust face, and you see how much elliptical drop you're going to have at what degree. And so that is determined by the piston manufacturer to how much drop they need for how they design the piston. Some are going to require deeper drops, some's going to require a lot shallower drops. The most common one is probably this C grind. It's called a clover leaf grind. You can see it comes in here, then it comes back out. And the reason for that, I'll show you a little bit later, is when you grind the piston, and if I had a complete round and I didn't go with that clover leaf, I would hit a little relief area and on the cast piston, and I would have to end up redressing the wheel over and over and over. So one thing that I like to kind of get along on center line of thrust, it's a basic, but at the center line of thrust face, you need to have your high point of your profile within 3 degrees of the center line. With Jasper, use 3 degrees total. And so a rule of thumb, if you can't check that, I would advise you to maybe go to, I don't know if you can see me, a corner of a piston and put it a degree, like 45 degrees is usually the nominal of what a lot of people did back then. So you would check here exactly at 45 and here. If I had a difference, then that will tell you if it's good or bad, if the center line has been pushed off or not. It was common, especially for grinders and hard cam lathes, because they had play in them, and it depends how you chuck them and how they were located before they did the grind. There's so many very things that I could tell you what difference that you need to consider. It'd be for your application, for a performance application. If I was building something that I really wanted the very best, if I had any more than probably 1,000th difference between those two, that would probably be the max I'd like to see. In general, for a gasoline engine, for a stock replacement and older model pistons, you could probably go up to 3,500 before you start getting concerned. I would put 2,500 for diesels because they have usually much less drop, and a lot of times they're a full round. Many of the early style Model A pistons, which I have some pictures of, and I actually got one right here. It's got a huge slot in the oil groove. This is for oil return, and actually a lot of people would call this a heat down. So the heat that would come from the crown will not go into the skirt. Therefore, you could have a very tight clearance to begin with. Most pistons were made this way for 50 years or so. And it's pretty good if the design will hold up for what you have. Let me show you a picture of it. There's an actual picture of the piston I was holding. This would normally be cam ground, but this one you see where the very top of this relief area, that is actually part of the diameter. Now, but when it was ground before, that would be recessed, and the same as this cast right in this area, so the grinding wheel wouldn't hit it. If you did, you'd continually break down the grinding wheel. So the basic design you have on a grinder is a straight taper. It would normally be from top of skirt to bottom, it could be 0 to 1/1000th drop that it would go down to. Also on this one, called, just as Dan said, this was extremely low horsepower engine to begin with. It very round, and it didn't have much of an elliptical drop. You got to have elliptical drop in the areas, so when the piston gets hot and expands and during operation, it's got to have much of a drop. If it doesn't, if you put a complete round piston in there, it would seize quickly as soon as the engine got hot. So it's critical to have that. Now, when the engines evolved from the full skirted design, you had the lower deck V engines with the counterweights, and so you had semi-skirt pistons. You see most of that prominent, probably in the 60s, 50s and 60s for the most part. You see a lot of those. I found one, a 396 Chevy, that I found a core on, and so I pulled the piston out of it. I'll show you. Now that's cam ground from the factory, and we'll go through the large turned radius. You also see this huge breakthrough slot all the way through here, where that's called a divorced skirt. And there's a little bit of a steel insert in that area that used to be used. So OE wise, you can see why this is called a semi-slipper, because you have a slipper here, because on some of the cylinders, your crank counterweight is going to be hitting in here. So that's necessitated it. So it's kind of neat to see some of these old things. It's the same thing. At the top of skirt, you're going to be, could be the same thing as you are on the size point. One of the biggest critical factors that caused a lot of problems with a lot of people, they didn't measure on the largest stiff area of the piston, and that's this point right here. You go all the way across from the pin area right below it. This is not going to give. This is going to be your largest point on this piston. A lot of people would measure at the end of skirt or somewhere in here. Well, these things are very flexible, and they can go all over the place. Matter of fact, the basic rule was they have a 3.5 thousandths. They could be 1/1000th less, or they could be 2.5 thousandths greater than what the actual size point is. So if you ever had one of these things, you never want to measure here. You also start seeing the cam drops, the elliptical drops, getting deeper because as the horsepower increases and the piston gets hotter, that you're going to need more drop to it. So this is directly from Chevrolet. So actually, this is a piston here that we have. I thought it was pretty cool. When you take these pistons out that has these straight tapers, you'll notice a wear area is very thin, and this is kind of normal what they would look like. Actually, some of them would be wearing in this top area and then wearing at the bottom area, and not much here. If you see something like that, you know that it had too much clearance and the piston was actually rocking in the bore. But if you have one correctly, this is the type of wear pattern you will see. Unless it gets extremely hot, it may pull out a little bit further. But normally this is what you have. So you don't have really great contact area, And also, just to kind of note, you may have pulled out several small block engines, maybe like 302 Ford or some of the other ones that came with very long slipper skirts. It wasn't uncommon. Here's a 302, an old engine. It wasn't uncommon for those days. You may pull one out and find out one of the skirts has already broke, fractured off. It's been running that way for a long time. So, you know, we don't do that anymore. Now, as horsepower started to increase much more, for example, I've got a Grand National Buick piston that was actually ground, has steel inserts, and they have so much heat, they have to do something with those. So a straight taper profile wouldn't work anymore. So they try to find ways, and this is where some of the hard cam turning machines were coming in place. And what you would end up doing a lot of times, they would end up being what they call a sled runner profile. So let me pull that. So this is a 300 Ford piston. Also note, before in the 60s and 70s, this was cam ground. And so the top of this relief area would be cast where the grinding wheel wouldn't hit. Today, everybody should be turning hard cam or CNC turning. So you put it out full. So this is kind of what it looks like as a sled runner. As you had more heat into it, what would happen, you would pull this top area in of the top of the skirt anywhere between 2.5, 3.5 thousandths, and you would round it out, and then it would go to a straight taper. And then this is the same thing as your largest size, and this is flexible. And you know, the later it gets on, you see more drop because again, you're having more heat. And that also depends upon the application and how the piston is done. You can also see this piston doesn't have great big breakthrough slots as the early one. If you have one that has extreme amount of breakthrough slots, it's, you know, it's structurally weaker. So you really limit what you can do with it. In the 1990s, had a lot more horsepower per cubic inch. You had smaller bores, started putting longer connecting rods, reducing the weight. You started getting really short compression height. You had some with forced induction, turbocharged, some supercharged, and that means now I'm making more horsepower and I got less surface area upon the piston to try to keep it. And now you're trying to think also, I got thinner rings, so you're starting to get in the economy mode. You're trying to get the weight down. OEs are doing all this because they have to. And when you end up doing this, you created another problem. Now I need a small piston and I need to make that thing stable. So I went to a much shorter piston. I've got a barrel profile, so I can't run the same type of clearances. And I've got to get that profile great, because otherwise I'll have a piston that will rock, will not, and you will lose ring seal and you'll have blow by. So basically, a lot of people at first tried with the master cams, hard cam turning, and then actually the very best and the way you should go is the CNC, because then you can really put into what you want your drop at what area and the exact profile of the pistons that you want on there. It's much better than a hard cam, but a hard cam was an easy way to start trying to generate that. For an example, a few years ago, our pistons are supposed to be all CNC'd. Well, one manufacturer overseas decided to use one of their hard cam lathes as they do for their other public or other customers. And this is what you see. You'll end up seeing the areas that are worn, and they're like this is indicative of a hard cam. This will show you where they have to run a master cam that has exact piston profile, that has to be centered correctly with the piston. So when you turn it, you get it centered. And also now you got to make sure that your cam follower on the lathe will follow that profile. Now this one is usually, I'm sure is due to one or two things. Normally it's hard to cut a master cam perfectly steel to make it follow and to make it continue to live without a lot of wear, a lot of problems. So a lot of times you'll get some of them that are actually kind of milled and not cut evenly like an elliptical profile should be. And also you may have some that are trying to turn the machine too quick, or the cam follower is too loose and it's not following the piston shape. Some other things that you'll get from a hard cam that will end up doing that way if you spin it too fast and you do not have the follower in constant contact, you may have one side that's deeper drop than the opposite side, and that's usually because it's actually flying off the cam and then catching up later. But this is what we watch and make sure we don't have. Now the next piston, it's an LS piston. It's for a 6-liter GM Gen 4. Gen 5s is similar, what we end up doing, but you have to have specific profiles. A lot of this ends up making sure also about the piston manufacturers, how they run their process to what tolerances they can have. So we go through all that when we visit these people. You reduce, actually on this one, it just depends. Let me just show you the piston. That's the actual profile that we would run. Now that's horizontal axis is times 100, just so you can see it. But this is a type of profile that you will see common on today's pistons. This is a nice gentle one that works really well. So here's the piston that we're talking about. So when we get this piston, we'll make sure that it's in a CNC machine. It's located off the bottom and chucked up. And so why we want to do this is get rid of all concentricity issues. If somebody takes a piston and they just turn the skirts and then they turn their lens somewhere else, then you can have a concentricity problem, and that will cause us problems. So we try not to end up doing that. So this is the actual profile of the piston. The size is, again, this is one of the largest stiff points that you have, 1.82. When you get to the very top, it's actually about 5 thousandths or so barrel drop right in here. And what we'll do on our prints, we will make models and we'll make prints. Then we'll send it out to our vendors and we'll send them the whole model so they don't have to worry about trying to interpret that. So we'll have every 50 thousandths what type of drop we want to have on that profile. After the size point, actually on this type, you really want to try to go in a little bit. That little bit, 2 tenths or so, will actually help create an oil wedge as power stroke goes down and helps lubricate the skirt a little bit better. If you had it flared out or more than what it should be and you just had it straight all the way down here, you would end up trying to scrape some of the oil off, and that's not what we're shooting for. Also at the same time, we'll contour the ring lands. So you'll see where the third groove comes. You'll also see where the second ring land comes, and then how it tapers up, and then how at the very top that will actually barrel that top in. The reason for that is, you know, if you put just a straight diameter piston in there to begin with on the ring lands, time it would heat up, then you would see top of the lands trying to be pulled. Many times in some of the old engines that you would tear down, you could see that, where you would see part of the top of the ring lands here, it's more scuffed than anywhere else. Our deal is we want to make sure, since we have CNC capability, can put anything anywhere, that we actually draw that in. So once it reaches optimum temperature, it draws itself out. Because the heat is going to be so much in the crown and the lands, it's going to expand further. So when you get this and you get the wear patterns down, then you got a really nice piston to be able to be stable. The deal is to make sure that the ring, the piston is stable, so the rings are square in the bore and seal better and reduce blow by. This is, it looks like a 3/6 piston GM. This is kind of like a normal wear pattern I'd like to see. So it's not straight like the straight taper breakthrough slots are. We actually like to get to where I really able to get kind of almost like a rainbow shape, and it helps that piston be stable. And when I get down here to the largest area, I've got a lot against the wall, and then the rings. One of the key areas is making sure the ring groove side clearance is as tight as they possibly can be, because the rings actually help hold these pistons very stable at crossover. So the worst case condition is this. So under a heavy loaded truck, pulling a camper, pulling a load, and it's really going, this is the heaviest pattern that I would desire to see. This still work, it's still doing its job, but this is where you really mess up. This type of design, I put an X design, it's a pretty good design. Any piston, whether it's a box, where it's an X, wherever it is, once you hit over here in these areas, they're stiff. So this skirt area in here is flexible, but as it goes, and as soon as it goes in this area to where this is at, that's where you start scoring. And that's where you'll have corner scuff to begin with. And you can tell that the major thrust side is going to be much more damaged than the minor thrust side. And so this is where you either didn't have the clearance, you had it too tight, or you overloaded it, or the engine was overheated some way. And so if I was going through this application, this is what if we normally saw, then you would try to fix that with a profile. Put a little bit more clearance, do a little bit more of the drop, and maybe come in a little bit more at the top. So today, pistons are so totally different, so much more horsepower. It's kind of funny today. I was one of the guys that works with me. They're actually checking a 255. I think it's a Ford Boss Cobra 2, 1978. I think that poor little thing put out like 105 or 115 horsepower or something like that in that heyday. And then we come to a Ford 3.5 Ecoboost today. This is just the first series. And, you know, this thing is like 420 foot-pounds of torque, 365, 370 horsepower. But you also see that you have a lot more issues with this, because this is one that is critical, that has a lot of detonation problems. A top ringland breakage, second ringland breakage. So you have to pull out all the stops on this to make these things live. So if, just for an example, I have a series of pistons here. This is Ford's first piston that they used. And there was a lot of problems with this, because the course would come back in the second land and the major thrust is broken through just heavy detonation. The 2011-12, they turned around, they used the same piston, but they anodized the top ring. When you anodize the top groove, what you do is you harden that, you oxidize in a controlled way. And so now if I had micro welding from the piston to the ring, then the anodization will help stop that. Continue, we get cores, and these are broken too the same way. So the last event, they actually put a steel non-resist insert in the top groove, exactly like a diesel. So that works really well. You're not going to have a second ringland breakage. But one of the problems is, you know, you're looking for as much mile per gallon as you can, and you're trying to get as much horsepower as you can. And then you have a lot of different direct injection and things like this. Well, it may be good for the OEM because, you know, some of these things are really hard to rebuild, and oil consumption can be very heavy with this. So our customers, we actually are looking at two different things from OEM to an aftermarket. So we have to take that in mind. The problem with this one was, from OE level, they put a 1.2 millimeter ring in here, and if I look at the surface area, the whole idea of the piston is to heat the piston crown goes to the top ring basically goes to the cylinder wall, and that's about 70% of the cooling that you'll end up getting. Well, when they anodized the top groove and didn't change the ring or the location, then, and it was still scoring and still scuffing, that tells you that I've got too many heat BTUs in the top ring and it can't cool itself enough. So they put a steel non-resist in here. I will not have the catastrophic failure, but they didn't change the ring and didn't change the area, the location. So this won't fail like it was before, but the top ring will still scuff. So that's where this is ours, and this is where we'll come in and do something completely different. So this is a forged piston. We use forged pistons for this one. We anodize the whole crown. We make sure that we use different ring packs. So I got a 1.5 millimeter ring here with the radial wall and all that. I have probably about 38% more surface area. So I'll have quite a bit more BTUs to be able to conduct to the wall. Also, if you probably can't see, but you know, I pull my ring down a little bit more. For one reason, if I do all this shaping and try to get rid of dead air space at the top, then it's great. So the ring doesn't get as hot. Also with the forging, and especially with it anodized, this will probably run 130 degrees cooler than what the OE would run. These are some of the things that we have to do. You also see the surface area of the skirt is larger. I like to end up doing that to make sure. So if I got the same amount of strength, I've got a lot less time to scuffing or potential for scuff because I've already turned around and increased the surface area the same amount. Also, one of the biggest things that we see OE on a lot of applications don't have much strain back. So this one initially had 4 oil holes that would go through. We have 14. Our deal is, as Dan said, when they were asking about why you have the bearing tanks, OE's looking for a way to make sure that you're trying to cut every cent that you possibly can. We in the aftermarket, we don't want any comebacks. We're looking for our customers and repeat customers, so we got to do something a little bit better. After 2000, it seems like the rings got way too thin. There's a lot of issues with OE. A lot of stuff is not surviving as well. Oil consumption is the biggest deal, so we attack that. You have several companies out there that has, you know, would say that, I know Subaru, actually, we talked to them a few years ago off one of their Foresters. You know, I really pinned them down, it took me a long time, but basically they don't consider anything excessive oil consumption if it's more than 500 miles to the quart. And that's actually in their owner's manual. When you start going through this, you'll see more and more of this go by where, you know, it's 1 quart per 750 is acceptable. Maybe like a Chrysler Pentastar where initially they'll say 1 quart per 1,750 miles, but after 50,000 miles, it's 750 miles. So these are the things that we got to make better. So we do a lot with the bearings, we do a lot with the different coatings, we do a lot with the different rings and designs and pistons. And with that, it's really critical to get these profiles just right. So that is the piston we're talking about. This is actually the Ecoboost pistons that we produce or have produced. This is the barrel profile. This is the size area. This is the deepest curve that will be. Well, the drop, if I can take the heat more to the top, I don't have to have as much drop. So when we test these engines, we test all these designs. Basically, I adjust the profile to make sure I've got that wear where that's normal and where that would be the very heaviest we'd see. We put them through a rigorous dyno test, 50 hours, maximum at 25 hours at basically maximum torque, between wide open throttle to idle. And the same thing with the last 25 hours, we actually do it at max horsepower plus 6%. So these are the things that must be done to make these things live. And the last page that I just put on is just to kind of show what our nomenclature or what the common terms and how to calculate a compression ratio, and actually made this and sent this out to all our folks. So no matter who's on the shop or what group leader is leading or what R&D, we're speaking the same language and trying to understand. So I try to go through that quickly. And so if you have any questions, I would love to discuss them or answer them the best I can.
Yeah, super, Russ. Thank you. That was excellent, excellent presentation. A lot of good props there. It's nice when you can have show and tell and actually show people what it is you're working with there. So that was very well done, for sure.
Well, it's hard not being face to face, but
yeah, no, doing as best we can virtually. Let's put it that way, for sure. Couple questions have come in. There's one here. What amount of rock is allowable for a given ring thickness before blow-by becomes an issue?
I'll look at no rock. Actually, a lot of our pistons, we have two different types of skirt coatings. And also, let me tell you, we basically run HyperEutectic for most engines, gas engines. That's SAE 390, 18% silicon. That's it has lower thermal conductivity. You can hold them a lot tighter, and the sliding resistance is less. And the deal with those from OE, as you had to go to that alloy, which costs a lot more, because now you got to have PVD inserts to actually machine this, which costs a lot more than carbide. But the whole idea was that is trying to be able to push against a cylinder wall without scuffing more. My rule of thumb is if I have anything more for a HyperEutectic piston that takes more than 2.5 thousandths clearance, I'm going to induce a rock. And I would say that would be at a 1.5 millimeter top ring. If I had a 1.2, I would like to see a little bit less than that, probably 2.2 thousandths max. And just kind of let you know how critical profiles are. We're able to run our forgings, which are 4032 alloy for all of them, in our HyperEutectic with the same clearances. So we're running forgings at 1 thousandths clearance minimum. And then we got a skirt coating on top of that. For our forgings, like that Ecoboost, we actually use an abradable coating. So when they actually put it in, it's using an interference fit. So it's extremely critical to try to get these things where they don't rock. And that's where the profiles are so critical to get that correct. And also with the same thing, we induce an upward tilt on the groove because that will actually seat the rings better. And then we do a minimum clearance on the side clearance of the top ring. Usually getting down to 1 thousandths, so between 1 thousandths to 2.5 is max if you want to use. That's another big issue that a lot of people forget because there's a lot of aftermarket. You'll go in there and they'll find out maybe with a 1.5 millimeter, they will end up cutting like a 61, 61.5 groove. In reality, it needs to be around 59. So all that stops that rocking. I hope that helps.
Okay, excellent. Thank you. Another question's come in. Where's the best place on a piston for when you have to balance it?
That really depends upon the design of the piston. Let me pull, can I pull my, let me pull this back up again.
Sure.
See if I can get one. So for these, you almost forget it. You got to go somewhere on the inside of the fin balls, but you're not going to have that problem. But when you get to these, it's always on the bottom. And that's why those side pads are also there. That's where they balance the pistons at. You probably don't have that these days, and you're looking at the newer pistons like this. Again, you would find something on the inside of the area of the boss area that is non-critical. The biggest thing is you want to make sure that you don't leave something with a sharp edge. You don't want to wait an area for crack propagation again. Let's see. This piston would be the same thing. The areas that you would want to cut a piston like this may be in this area right here, not much, radius it, and then you'll also have some pin boss area on the inside. If you have excessive head thickness, which more than what it means, then you can cut that out also. If you're looking at a performance piston and you have a shop so you can cut it, especially if it's oversized, you can cut on the interior of the wall of the piston. And realistically, for a gas engine piston, you'd want that wall to be probably around 90 thousandths minimum. But you can do all that. It just depends upon your type of piston. A lot of forgings, you know, they got a certain amount of blanks. You can make several pistons. So you can cut a lot of that off from the head area.
Okay, yep. All right. Another question for you, Russ. How much first ringland thickness do you recommend for higher boost turbo builds, like more than 30 PSI, for example?
So much in the ring that you got to look at. It's a big deal off material that you use. You know, in the old days, it was cast iron. You know, they wouldn't last no time. And then they went to ductile iron, which was kind of nice. You got to have a minimum of steel. And if I had that, I would have a really good top of the line steel. I could tell you different alloys. Then I'd probably have it nitrided or PVD coated on the outside. And if I had a boosted application running that, I would want to make sure my radial wall is probably like 120 thousandths or more. And I'd have probably run a minimum of 1.5 if I was running that much boost. One of the biggest deals you got to make sure, because you're doing so much heat, you got to have enough area, as I told you before, to make sure I have enough heat that I can transfer to my cylinder walls. Now, if you're just drag racing and where it's a few seconds, you can get much less than that. That's why you see all these really extremely thin pipe rings these days in drag racing. It's really easy to survive in 4 or 5 seconds or 6 seconds, whatever you're trying to run. But if you want something to drive on the street or to put a lot more miles on, I'd recommend 1.5 if I could do it.
Okay, all right. Another question for you. Shops are dealing with coated pistons, and sometimes there's not a mic, like a mic point or a measurable part on the piston to measure. What's your recommendation on measuring a coated piston when you apply it to clearancing to the cylinder?
Well, this is why I hate to, but we always, to keep our vendors honest, we put a size point where it's uncoated in the largest area of the piston, really where you really want the coating to be at, but trying to make sure you get the right clearance. This is what we have to do. There is a couple of chemicals that people use that we actually have too that can actually rub part of the coating off. One of the biggest things, if it's a spray-on coating or if it's a silk screen coating. If it's a silk screen coating, you'll have an edge to the side that you can measure. So what I would end up doing is find out the difference, the thickness, close to the size point if it's silk screen. And then you can, you know, measure it that area and then back up. If it's a Mahle D10 or something like that, spray coating, usually you won't find those over half a thou thick. So in what we used to say at Federal-Mogul a lot of times, a skirt coated piston, it was really a thousandths if I added on diameter on the average. Now, if you send it off for somebody else's spray coat and maybe do different abradables or something like that, you got to find out what thickness they actually did. But most of the ones you'll find out are probably a D10. If they're overseas and they're maybe colored green color or something like this, you may find out that that's only like 2 or 3 tenths thick.
Okay, excellent. So another question then, kind of to follow up with that, is it normal for the coating to be worn off after a certain amount of mileage?
Yes, what you don't want to do is see something that's flaked off. One of the biggest problems that encountered with EPA probably about 10 years ago. Some of the cleaners to use to clean the pistons and really get them clean before coating was basically outlawed. So some of the cleaners that they're using these days doesn't get them as clean. And if you have anything that flakes off, that is due to the piston not being clean and get all the oil and residue off before it was coated. That's one issue. If I had a D10 and only had 4 or 5 tenths, you could see where it would be rubbed off, but not all. Just you should still have it in your turn grooves where you can see it. Should not all be wore off. If you have an abradable coating, if you have it correct, it will wear, but you shouldn't wear it off. Probably what you're seeing most is a D10 type situation, screen coated, and some of those areas wear off or they wouldn't apply very well.
Okay, all right. Another question, Russ, has come in and they're asking, what makes a piston HyperEutectic compared to eutectic?
HyperEutectic is anything over 12.5% silicon. When you get over 12.5% silicon, it's kind of like, I always used to think, if you were put sugar in water and you continue to stir it, and the time that you can put too much sugar in there and you cannot dissolve the water, that's like a HyperEutectic. So HyperEutectic actually has raw silicon particles. And it was kind of funny when General Motors was first coming out with the Cyclone and a few others, they were HyperEutectic. But because they didn't want to get deep into HyperEutectic, they only put it like 13%. Well, that made a very weak piston and they broke a lot. So for a while, they actually got our aftermarket pistons and put them in and to make them work. So HyperEutectic is a totally different creature, but your question is, most all pistons before 1990 was a hypoeutectic. That means it was less than 11% silicon. Normally it's 8.5 to 10. And when you got a eutectic, that's like a 40-32 alloy, which is 12.2%. So anything between 11.5 to about 12.5 is eutectic. Anything that has raw silicon particles over 12.5% is hyper. All
right. Okay. No, super. One more here, a couple more. Actually, we got lots of time for questions still, folks. So here's a question for you, Russ. A resist insert. Could you explain what it is and what its purpose is?
A resist insert is what diesel actually used in the top groove. That's what I showed you on the last Fords and the new Ford 2.7 and the 3.5 series 2 has a steel resist. That's exactly like diesel, the top ring carrier. It's getting so hot in that area that you got to have an insert, but you got to be metallurgically bonded. So there's a process that you got to get that nickel resist insert, usually use hot tin, put it in and cast it. And then you got to have a diazyglo or some type of ultrasound to see that you got 100% bond. One of the biggest problems with resist insert, you can make one look good, but if you don't have a complete 100% bond later on, that will break and come out. So it's really critical that you have somebody that knows how to do those, manufacture your pistons and use those. Now, that's a resist. Now, you also, in the old days, you had autothermic inserts and different inserts in the side of the pistons that people may think about too, and that's a totally different reason.
Okay, so I've got another one here I just found that also has in regards to inserts. So why aren't steel inserts used in gasoline engines any longer?
Well, this is probably one of the last ones that I saw use it, turbo Buick of the 80s. Steel inserts were used to control expansion. So in the old days, when you only had grinders and straight taper profiles, you were really limited off what you can end up doing. So if you put a steel insert inside those, let's say like that 396 had, pull that up. This area has actually got a little steel insert in there, and that's this area here. What happens is, since the expansion rate is 3 times more with aluminum than steel, if I pour those in, it actually makes a mechanical bond. And so for about 200 degrees, that drop really won't hardly change. And so you can actually run a little bit tighter clearance. You don't have to run as deep a drop, because in those days, you had such a poor wear profile, it was easy to get an engine knot, piston slap. And you also notice in the old days, they used to have the pin bore off center extreme, like 120 thousandths or something like that off center. And that's to stop that crossover knot. Actually, people always thought, well, or a lot of people come to me and said, well, that makes the piston stronger. No, it makes it weaker. It's not a metallurgical bond. If you cut those out, you'll find porosities in areas that's not there. So that's why you see these days, besides weight, besides savings, you know, in the advent of CNC, you do not want steel inserts in your pistons and make them weaker.
Okay.
Makes sense.
All right. Yeah, that does. No, for sure. So kind of going back to this, the skirt coatings again, you know, do you need to add more piston to bore clearance to compensate for those skirt coatings?
Absolutely not. Skirt coating, for the way that we use it, and we use several different, but basically a D10 or an abradable type. That's why if we'll run 1,000th minimum clearance on our forgings or castings in a gas engine, and depending on what we allow it up to and what our tolerances, we may get up to 2.2 or 2.5 thousandths clearance at the max. But that's the true size to the aluminum. The skirt coating we don't count. So if I'm able to put a 0.5 thousand skirt coating per side, such as a D10, I just really help my clearance by 1,000ths. And you do not need to measure for that. As I said, our abradable, most of our abradable coating goes in is actually interference fit. They slide in nice. They work really well.
Yeah, and honestly, that is a question we get on the tech line all the time as well, because I mean, a lot of the OEM specifications almost show an interference fit as the spec, and we're often questioned, you know, how am I supposed to drive a piston in when it's interference fit, you know, and so
it goes in easy. I mean, there's not hardly any more pressure going into it. It slides off real good. You got to remember, you're dealing with a Teflon type low coefficient expansion that will slide off pretty easy. You got a chamfer in the bore, so it shouldn't be a problem. Now it makes, you know, I had to talk to everybody here when we started using abradable, because oh, this is too tight. No, this is fine. We've already used it. We run these things in engines for 10 years without you knowing it, and going through testing, they work really good. They'll abradable, abradable will actually come off and make its clearance.
Okay, so this question, it's sort of to do, is that coating hurting any, like if that coating's coming off, is it hurting anything in the engine, or is that normal? I mean, will it just get absorbed in the oil? You know, what is it I guess they're asking is that coating something that can cause harm, whether it be an abrasive or something like that?
No, you know, that's a good question. A lot of racers talked about this, and they wanted their engines kind of broken in on the corners. So because they thought that they had a little bit of a horsepower decrease initially until it was broken in. But no, like I said, when you use a D10 or skirt coating or something that's still screen on, they can be as thin as 3/10. They can be as thick as 6/10. And when you're looking at a graphite base such as that, it's not going to hurt anything. It's not going to clog anything. It's not going to stick or ring. It breaks up. Abradable, it just smooths out really easy, so you don't have big areas to flake off. So no, I'm not worried about it, and I've never had a problem with those.
Okay, all right. No, that's good to know. All right, another one for you, Russ. What are the limits of adding piston to wall clearance with later model gas engines with these short pistons, thin rings, and the barrel type skirt?
This is why we put so much into it, because if you look at this short compression height, when things starts getting about an inch to 1.1 inch at an OE level on a piston, then you got a barrel profile to it, and you use well, I'm gonna run it 1/1000th and a half or 2/1000th. You know, that could rock pretty easy if you don't have the correct profile. So that's why I'm really particular on running the late model engines and getting these profiles correct. If you do that rainbow shape, as I noted before, that stops the rock. If you have the rings where you got the waviness under control, where you don't have any more than 3/10 waviness in the grooves, and you're running 1/1000th so side clearance, that stabilizes those pistons a lot. And then when you put skirt coating on it, you know, that is my deal. I mean, the biggest deal for the last 15 years or so is oil consumption of these engines, because the OE has went really small on the rings, and so they don't seal well. Our issue here is to make sure that we know our customer is more on the heavy side on trucks and things like this, or performance apps. So we need to make sure that that piston does not rock. And that's why we do all these profiles, to make sure it's right, because I want that ring sealing quickly and not to be rocking. And if I rock a small face ring, you know, you just lose ring seal and it wears so much quicker. So that also gets in the ring materials and things.
Okay. All right. Another question, Russ, and this is kind of diesel related. They've asked, in some instances with piston protrusion specifications, there is no head shavers or head saver shim available. Is it okay to machine the top of the piston if needed?
Most, yes. We actually do that on a few. What we make sure of, if I've got a nice combustion bowl and or any release areas, that we don't make those sharp. One of the worst things you can do in a diesel that has a nice diesel bowl into it is come out with a sharp edge, because as injectors go, you'll have over time, you'll have fracturing from thermal cycling. So we do things for some performance engines that we do for a customer, 800 horse Duramax. And all these things, we go ahead and what we call de-lip those areas and make sure that bowl is nice and smooth to try to prevent some of that. Normally, the most that you can probably ever cut off a diesel piston without having a problem is going to be 10/1000ths, most generally 5.
Okay. All right. Yeah, and you know, sometimes that might be just enough. Just again, there's just no other options with thicker head gaskets or head shims. So it's good to know that that at least is an option out there for sure.
And what we also do, we work heavy with a lot of some good head gasket manufacturers. Konecnik is one that I really like, and we always will have, especially when you're looking at aluminum blocks and aluminum heads, and you've got something hot and you're trying to save it and get the deck height correct. And I got much higher compression ratios, so you got to get these things right. That's where some will have 3 different type of head gaskets, even for gas thicknesses, so we can do so. We work, and like I say, one thing around here in the U.S. is Konecnik does a really good job on that too. And that helps us at a quick turnaround. But there's not probably a new engine we come out with that don't have a couple different thicknesses head gaskets. And we do the same thing with the diesels. We make sure we got at least 2, if not 3.
Okay, super. Well, Russ, that was an excellent presentation. Really, really good. I mean, this is information that, I mean, you're digging into stuff that the shops just don't get a chance to see all the time. So I'm glad you took the time to free yourself up for this. And again, I mean, this is going to be recorded, and I know we'll be passing out this presentation to the schools and that kind of stuff. I mean, this was great information, so I appreciate it. Thank you. very, very much.
You know, these were just some of the basics. Like I say, if somebody calls and needs something or they got something more in depth, I'd be glad to try to help them when I can.